In this video, we'll be looking at attaching rectangles to a object such that we are attaching them parallel to the y-axis. So the first thing, again, we always have to do is set up the actual region that we're playing with. The objects that we're bounded by are y equals x squared and y equals 8 minus x squared. So when I go to graph these, the first thing I got to do is, again, I'm going to be up here 8 units higher based on this function, and it's going to curve down. And the second one I have is going to be starting at the origin, which is x squared, and it's going to be facing up. So it appears as though the region that I'm attaching these rectangles to is going to be in this space right here. And again, I'm attaching them parallel to the y-axis, so I should slice this thing in terms of, again, dx. So I'm going to have an integral of an area function, which is the volume, from x equals, and now I've got to figure out what these two intersection points are, where this function is clearly on top of this function on the bottom. So I'm going to go ahead and label these very clearly. This one's on top, and this one's on the bottom. Okay, so if I need to label this one's T, and this one's B. So with that all identified, it's important for us to note that the distance from here to here is simply going to be the top function minus the bottom function. So that is that distance that we're looking at that I'm going to have to make note of for later. Now let me go ahead and reread this particular question. Assume that the rectangle is attached by its shorter side and that the length is 3 times its width. So that means that if I'm going to look at the rectangle, I know that I'm going to have length times width for the area, but more importantly, that length is 3 times the width. So if I go ahead and leave the width there, and I'm going to do 3 times w, that means I'm going to have 3w squared. This would be the area of the rectangle, or each rectangle, that I have to attach to this object. And the other important part is that it's attached by its shorter side. So that means we're going to have this long rectangle coming out of this object. And again, every single time that the object is a little bit longer here, the rectangle is getting longer out there. So that means the width is what's being attached. So I'm going to put a w down here, which again, we normally identify that w as s in most of the examples that we've looked at. But this time I'm identifying as a w. So now my volume is equal to the integral from, again, we've got to figure out what the bounds are by setting these two functions equal to each other. So I'm going to do that down here. X squared is equal to 8 minus x squared. I'm going to add the x squared to both sides, giving me 2x squared is equal to 8. I'll divide by 2, giving me x squared equals to 4. And therefore x is equal to plus or minus 2. So that means I'm going to start at negative 2. That's, again, the lower bound. And I'm going to go to positive 2. That's the upper bound up here. So now I've got to figure out, again, what is the area formula that I'm trying to evaluate. Well, we've already identified that the area of each rectangle should be 3w squared. Secondly, we've already stated that this w distance should be the top function minus the bottom function. So very carefully, I'm going to do this in 2 steps. I'm going to have 3w squared in respect to x. Now again, I can't integrate this because w is not the function of the variable that is supposed to be in this integral. It's supposed to be in terms of x. So the second detail that I have to do is I have to first identify then that my w is not actually w. My w is really, again, the distance from the top function minus the distance of the bottom function. So that means it's simply going to be this right here, which is 8 minus x squared, that's the top function, minus the bottom function, which is x squared. So that's going to provide me with an overall function of 8 minus 2x squared. So that is what's going to go in this system. So unfortunately, I'm going to have to FOIL this out and distribute the 3, which is going to provide me with an integral of x equals negative 2 to 2 of, it looks like, 3 times 64 minus 1632 x squared, and then plus 4x to the 4th dx. So having this integral and distributing that 3 first, then we can integrate each term separately, plug in 2, and then plug in negative 2 after integrating. So that's the setup to evaluate the volume by attaching rectangles that have a 1 to 3 ratio of, again, width to length to this object.